Hello friends, today I'm going to show you how I've programmed this nice little solar system demonstration. Here we have a sun in the middle and a few orbiting planets with nice little trajectory tails and not entirely circular orbits. This one in particular is looking a little bit elliptic. So I'll show you how I made all of those features and how we programmed this solar system using real equations of motion and physics that affect our universe and our solar system. Let's get started. So I have an empty sketch here that just creates a canvas in setup and then sets the background color. So far that's what this looks like, just a gray square. And we're going to need a class for our celestial body. So I'm going to come down here and say function body. And what does a celestial body have? It has a mass, a position, and a velocity. So position and velocity, even though they're coming in as a single argument each, these are going to be vectors for position and velocity. And we can load those in. This.mass equals mass under mass, this dot pos equals under pos, and this dot vel equals under vel. We also have a radius. This dot, let's say r equal, I will just make this a function of the mass for now. And we need a function to draw this body. So this dot show equals function. And I'm going to make this an ellipse at this.pos.x, this.pos.y, and we're going to make the radius this.r, this.r, so it's of course a circle. And why don't we no stroke and fill 255. So this function will draw our celestial body, but we don't actually have any instances of this object in our sketch. So let's just make the sun. I'll create the sun up here, and then in setup we can say sun equals new body, and we're going to center it. Well, let's just give it a mass first of, let's say, 100, and we'll center it. Create vector 0, 0, so it's in the center of our sketch, and create vector 0, 0 again, because we don't want our sun to be moving in our sketch. Alright, and in function draw, we can say sun.show. So now, we have our sun up in the top corner here. This is actually the coordinate 0, 0. So what we need to do is translate the sketch so that our sun is in the middle. Every time we are in draw, I'm going to say translate width on 2 and height on 2. Beautiful, look at that. We have a sun in our very empty and cold universe. So let's give it some planets. Here's the sun. I want to create a planet at some radius from the sun, and also at some random angle, so that this planet could appear randomly on the screen, but I want the units to kind of be in terms of this angle and this radius. So let's first create the planet. And in setup, a planet is just another celestial body. So we're going to be saying planet equals new body. It's going to have some mass. Let's just call that 25 for now. It's going to have some position. Let's just call that planet pos. And it's going to have some velocity. Well, for now, I'm just going to say 0 velocity, so we can just understand things for now. Let's just create a static planet at some position around the sun. Well, in terms of this angle is easy enough. We can just pick a random angle between 0 and 2 pi, and we can just pick a random radius. So we'll do this in terms of polar coordinates, I guess. Let r equal random. And what's our minimum? Our minimum could be the sun diameter or the sun radius. Let's just say the minimum is sun radius, and the maximum is the window width. But divided by 2 because our sun's in the middle. So our planet's going to appear somewhere between the surface of the sun and the edge of the window. And let theta equal random 2 pi. And now we just need to translate that into Cartesian coordinates. Let planet pos equal create vector, and x is going to be r cos theta, and y is going to be r times sine theta. Nice. So, to recap, we've created some random position based off a random radius and angle, and then we're just creating a planet at that position. So in function draw, we can say planet.show, and if everything's worked out, hey, hello, I've got a little planet down here. Let's refresh the sketch. It seems to be missing. Let's refresh the sketch a few times. It looks like, you know what? I've taken the window width of the entire window, not just the sketch. But, I mean, I was going to do that anyway, so why don't we just go back to our sketch and create a canvas to the whole size, window width and window height. Okay, let's see what we got. This is looking quite nice. I'm just going to refresh the sketch a bunch of times. Yeah, we've got our planet appearing here and there. Now, interestingly, because this is a rectangular screen, the planet is probably going somewhere out here or somewhere down here. So what I ought to do is take the minimum of window width and window height. Does that make sense? That way we're always going to be on the screen. Wonderful. Okay, we can generate a planet anywhere. All right, and that's just always going to be on the screen. Perfect. Now, of course, this is a solar system. Things are going to have to move at some point. So let's build a little simple physics engine to get this planet to move. Down in body, I'm going to create this dot move, I guess, equals function. You know what, this dot update, because maybe it'll update a few other things. This dot update, so we want to update the position, and that is really just saying this dot pos dot x plus equals this dot vel dot x, and this dot pos dot y plus equals this dot vel dot y. Okay. So that is just going to increment the position by the velocity. Now, if we initialize our planet with some small velocity, I'm just going to say, you know what, I'll make it asymmetric. I'll make it 4,2. And in draw, I can now say planet.update. And this should update the position of our planet. And there it goes. And again, and you'll see it's drifting off into the dark, cold reaches of space. How about we give it some gravity to keep it in orbit? So to apply some kind of gravity, we're going to use this universal law of gravitation equation, which is F equals big G times m1, m2 over r squared. What this means is if you have two bodies separated by some distance r, and they each have a mass, it means that the force that attracts them together is going to be equal to the universal gravitational constant multiplied by the two masses. In this case, m1 could be our sun, m2 could be our planet, and r squared is just the distance that separates them. All right, that's kind of a lot to to figure out, but suffice it to say, we know that there needs to be some kind of attraction to the sun. So I'm going to create an attract function, this dot attract, and we'll start from there. Since it's the sun that's going to be attracting, we're going to add the argument to this function called, I guess, child. So when we call this in draw, we're going to have sun.attract planet. So then when the attract function gets called, child is the child of the sun, it's the planet. So let's let r equal the distance. And it's the distance between the sun and the planet. This dot pos dot x, this dot pos dot y. So it's the distance between this vector and child dot pos dot x, child dot pos dot y. Okay, now that we've got r, we're basically ready to calculate f. Let f equal. Now f is going to act in the direction towards the sun. So we can initialize it as some vector that points towards the sun. This dot pos, and we need to copy that so we don't actually affect the position. This dot pos dot copy, and then we want to subtract child dot pos. So what we're doing is creating a vector that points from the planet, the child, to the sun, which is in this case the this. So that's not actually what f is going to be. This is just basically setting it to point in the right direction. Now we can say f.setMag for set magnitude, and this is going to set the magnitude of the force. And that's what this equation is for. So the magnitude of the force, g m1 m2 on r squared. So that's going to be g times this dot mass times child dot mass, all divided by r times r. I'll just wrap those in brackets as appropriate. Okay, so we don't actually have a g constant yet, so let's just create that for now. I'll make that 1 for now. So we have some way of finding the force F, but we need to actually affect the planet with it. So we need to extend our physics engine. This dot apply force equals function, and the force really just affects the velocity. It's the same as this equation, except now it's acceleration affecting velocity. So this dot vel dot x equals, and if f equals ma, then a equals f on m. Well, we need to pass in our f divided by this dot mass. And I can duplicate that. This dot vel dot y, and of course this should be f dot x and f dot y, because f is a vector. So now that we can apply a force to our planet, let's do that with our calculated f. Hang on, that's way off. Hang on. Child dot apply force, and we want to apply f. Alright, we actually have, I think, the complete physics engine for a solar system. We have the sun attracting the planet, so we should be able to run this and see something if everything works. Looks like we've got an error. What's going on? Oops, this should be adding those components, not just setting it equal. Okay, what's going on? Looks like we've still got our initial velocity. I'll just turn that initial velocity off for the planet just to see what's going on. And you can see it's very slowly falling towards the sun. Poof! And then it hits the center of the sun and just shoots off because of, I don't know, that looks like some kind of dividing by a very small number. But we have real physics, real gravity affecting our planet. Isn't that cool? If I turn up the universal gravitational constant by an order of magnitude, then gravity is now much stronger. But this isn't quite right, is it? We want our planet to orbit the sun. We don't want it to just fall towards it and shoot off. Here's the situation. We have the sun and we have the planet. And at the moment, the planet's just falling into the sun. Now we know what radius the planet is at because we set that. And to get it to orbit the sun, we're going to need some velocity this way. With some initial velocity at right angles to the radius, we'll get some kind of orbit. It might still fall into the sun. It might be this really big orbit. But we actually know how to calculate this to get a circular orbit. And that is using, this is the orbital speed wiki page. There's a mean orbital speed that we can set, which will give us a circular orbit. And that's this equation here. V is equal to the square root of big G, that's our universal gravitational constant, we've used that, m, which is the mass of the sun, and r, which we've set. So let's apply this formula. This is for the initial velocity. So here we had the planet position, and now we're going to set the planet velocity. So I'm going to create a new variable, planet vel, and I'm going to make that equal to planetpos.copy. This is because we know we want the velocity to be at right angles to the position vector. So I'm just going to grab a copy of the position vector and then say planetvel.rotate by half pi. That's 90 degrees. So we have some vector pointing in the right direction for a circular orbit, and now we just need to set the magnitude. Planetvel.setMag, the square root of g times sun.mass, all divided by the orbital radius, which is planetpos.mag. Let's have a look at our solar system. Okay. Oh, of course, we haven't actually set the planet velocity. Hey, look at that. I'm just going to turn G up a little bit, and by a little bit I mean another factor of 10. And look at that. We have a planet orbiting the sun. Take a moment to appreciate what's going on here. Even though we've got these masses and these radii that are kind of like arbitrarily chosen, even the universal gravitational constant is chosen, because the law of universal gravitation, the force equation, is just this very simple expression that uses just some constants and properties of the system. And the same with the orbital speed. Everything's locked in. We have the real physics for gravity and we have the real physics for the orbital velocity. So it doesn't matter that we chose like nonsense masses and nonsense distances. This holds for this circular orbit at this scale. Isn't that, I think that's pretty amazing. Now, of course, one planet isn't very exciting. How about we increase the number of planets in our solar system? Now, instead of let planet, I'll say let planets, and I'll make that an empty array. And when we create a new planet here, we'll put that inside a loop. Let I equals 0, I is less than num planets, I plus plus. And we'll take all of this, put it inside the loop, and now we have to say planets.push. So we're going to be pushing new body objects onto our array of planets. And we need to do the same thing in draw. For let I equals 0, we're going to loop through all the planets. Planets.length, I plus plus. We're going to say sun attract planets I, planets I.update, and planets I.show. Now we don't have a constant for num planets yet, so let's create that. And we'll set that to 5 for now. Look at that. We've got 5 identical planets orbiting at various radii. That's pretty cool, but I think we can make this look a little bit more natural. How about we change up the properties of the planets a bit? Let's start with that. So where we create the planets, we can actually give them a random mass. This first argument is mass, remember. So we could say random, we could give them a mass between 5 and 30. That could be interesting. Okay. Oh yeah, this is a good example. We've got this tiny little planet orbiting around and a few bigger ones. Ah, this is a bit more interesting. Look at this. Okay, so we've got various sized planets, but I think we can still do better. So this is the situation we have currently. We have the sun, a planet orbiting it at distance r, and the velocity to make it a circular orbit is some function of r. So if we take this velocity and we just decrease or increase its magnitude, we can change the shape of this orbit. If we have a faster velocity, then we're going to get an ellipse that kind of bulges out at the opposite point. And likewise, if we have a slower velocity, then the ellipse is going to come in closer to the sun. And as you can see, we can drastically change the shape of this orbit just by changing this initial velocity magnitude. So let's give it a go. Planet velocity, this is the initial velocity, dot multiply a random 1 minus destabilize, some variable called destabilize, to 1 plus destabilize. Now destabilize is going to be some tuning parameter that we can adjust. We can just set that to 0.5 for now. So it's going to steer the initial planet velocity some fraction below or above its current value. That is not defined. Destabilize. Okay. Cool. Oh, that's pretty interesting. Perfect. Look at this. We have this one right in the middle in a really elliptic, fast trajectory. The others, it's kind of hard to tell because they're so far out. Maybe we should tone this down a little bit. Let's make this 0.2. Okay, we definitely still have like some elliptical orbits going on. So that's pretty cool. Yeah, I mean, this is basically done. We have a real solar system with like realistic-ish orbits. I know the planets don't interact with each other and they don't really tug on the sun either, but this is a pretty good approximation. There's just one other little feature I'd like to include, and that's maybe some function to like trace the paths of these orbits, so they're a little easier to see the shapes of. Each planet is going to need its own path, so let's create a variable, this dot path, and make that an empty array. Now, every time the position updates, we can say this dot path dot push, this dot pos. So every frame, the position is going to be updated into path. But if we let this just go, path is going to grow unbounded. So we can then put in a check to make sure that path isn't too long. Otherwise, we're going to use up lots and lots of memory. So we can say if this dot path dot length is greater than, I don't know, 100, then this dot path dot splice at index 0 remove 1 entry. So this is just so we can keep our path at a constant length. In show, we can draw that path. So we can say stroke, and for let I equal 0, I is less than this dot path dot length minus 1, minus 2, I'm not quite sure, I plus plus. We want to join the points together with a line basically, and I'm not sure if I need to do -2 or -1 to make sure we don't get an error for trying to access a point that doesn't exist. This dot path I dot x, so we're going to join the current point to the next point. We're going to join a line from the current point to the next point. So that's I plus 1. So to recap, in the update function, we add the current position to our path array, and we make sure the path array doesn't get too long. And in the show function, we step through every element in the path array, and we just join a line between it and the next element. I don't know if you can see this, but every planet has a tiny little black spot in the middle of it. So the path is being made, but what I think is happening is here. I need to create a copy of this vector. If I refresh that, there we go. Now it's a little easier to visualize the trajectory of our planets. How nice. Well, you know, I just can't help myself. Now this is quite natural to have planets all going in one direction, but I just can't help but think we could change that. Where we have planet velocity, I reckon we could have the odd planet going in the wrong direction. So how about if random 1, we're going to roll the dice here. If random 1 is less than 0.2, so 20% of the time, let's flip the planet velocity. Planet velocity dot multiply -1. Is that allowed? I don't know. Let's find out. Hey, there he is straight away. We have 1 planet out of our 5 going in the quote-unquote wrong direction. That's pretty neat. Yeah, here we have 2 out of 5 going in the wrong direction. There, nice. What a simple little thing to change that, I don't know, makes things a little more interesting. We're quite happy with this result. I think it's quite nice and has a lot of potential. If you enjoyed this video, definitely let me know. I'd love to hear from you if you have any questions or any uncertainties. And yeah, thanks for watching.